Okay, we're recording. So welcome back. I hope everybody had a good Thanksgiving break. So we're just going to dive right in where we left off. We finished up talking about Gauss's divergence theorem last time, so we're going to move on to Stokes's theorem, the other half, sort of this enormous section 7.3 that we're in the middle of. Again, I switched the orders of those two theorems. The book prefers to do Stokes's theorem first. I and most other books prefer to do Gauss's theorem first. Okay. All right. So anyway, what you're going to notice, broad brushstroke, is that this is going to look really familiar. It's just going to be kind of one dimension up in the context. But Stokes's theorem is extremely similar to Green's theorem that y'all, of course, all remember, and we've discussed this at great length. In particular, the approach was with Green's theorem was to first talk about boundaries. What do we mean by boundary? We had to make sense, in particular, of what is the orientation of a boundary. We had to get precise about that. So, boundary orientations. Then we had to introduce this idea of accumulation. There was a bit more to say about it for Green's theorem because it was our first example of accumulation. But the punchline was that boundary circulation accumulates. And we drew this picture and, much discussion ensues. We pointed out that because of the accumulation property, you can think of boundary circulation as actually happening in the interior, and in particular, you can think of it as actually behaving kind of like a sort of a stuff. It's a stuff-like thing, at least in terms of how it behaves in the equations. So whether it's physically stuff-like isn't the point, of course, but it behaves mathematically like it's as if it's stuff, as if it's kind of like mass or something. And then, well, if that's the case, if we're talking about a stuff, then you can talk about stuff per unit size, aka density, right? And we gave that a name. I like to call it Green's operator, and this is the formula for it. The details of deriving of which are not what I want to focus on. And bam, we got ourselves a theorem. Right, that's how Green's theorem went down. Now, just to hit the broad brushstrokes before we dive into the details, Stokes's theorem is going to follow the same pattern. We're going to have to get real precise by what we mean by a boundary, this time for a surface in 3 dimensions. Right? But we're going to have to get precise about what we mean by boundary. We're going to talk about accumulation in particular. Again, it's going to be boundary circulation. That'll be the quantity in question. And we're going to find that it does indeed accumulate. We will conclude similarly. That means that boundary circulation, it behaves like stuff. Even though we don't think of it physically, mathematically, it behaves like stuff. It's accumulative, like stuff is. And correspondingly, then, you can talk about a corresponding notion of density. And with that notion of density defined, theorem. Right, so very, very similar pattern. The only thing that's different is a couple of details. And here we go. Okay, so pausing real quick. Why don't I pause for questions? If anybody has any questions about the big picture, the approach we're going to take here. Everybody on board? So again, the big difference is we're now in 3 dimensions instead of 2. Green's theorem is a theorem in 2 dimensions. So now in 3 dimensions, what remains, though, is we're still talking about a 2-dimensional thing. We're still talking about, in this case, we would call it a surface, a 2-dimensional thing in space. We call it a surface. Whereas with Green's theorem, a 2-dimensional... What did I just do? Oh, yeah, okay. A 2-dimensional thing in 2 dimensions is just a region, right? It's just some set, but still a 2-dimensional thing. Okay, so our 2-dimensional thing, still 2-dimensional, but living in 3 dimensions. All right, so what do we mean by boundary? First off, the surface. What do we mean by the boundary of a surface? I like to think of this in a couple different ways. For one, really the simplest way to think about it is it's where the edge is, But in order to avoid confusion with, creases or things like that, let me just point out that there's a different way you can think about boundary, and that is the boundary curve is where if you were to imagine that there were some ant crawling around on this surface, right? The ant can crawl around, the surface can bend upside down. Ants have little sticky fingers or whatever. They can walk upside down and any which way, right? And they don't even notice. Everything just looks normal to them. As they're walking along, there's left and there's right and there's forward and there's back. They're just walking along here until they get there, at which point they get very confused because they get to this point and they can't go further. Right? So I like to think of it as the boundary is where the ant gets confused. I think that's a nice, crisp, simple way to think about it. Okay. But what we really need to worry about is orientation. So if I have an oriented surface, here again is our surface. I emphasize this is an oriented surface. That means that there is a normal vector describing what is the positive direction through the surface arbitrarily. No particular reason, by the way, but arbitrarily I'm drawing this as a surface oriented upward. Given that oriented surface, what is the orientation on the boundary curve? Right, we've described where our boundary curve is. It's where the ant gets confused. But is the correct direction this way along the surface, or is it that way along the surface, and how would you decide? Okay, the convention I'm about to show you is arbitrary in a sense, but like all of our other boundary conventions, it's also very standard, and so it's not optional. Right? Arbitrary, but not optional. And here's the rule. It's a little bit of a weird rule. It goes like this. You start with your surface's orientation. Right? Oriented, in this case, it's oriented up. You use your right hand, thumb, in the direction of that orientation vector, defining the orientation of your surface. Thumb in that direction. Notice then your fingers bending the way fingers want to bend. Your fingers define what I'm going to call a swirl that goes around the normal vector. All right, now you'll notice I'm going to hesitate to call this clockwise or counterclockwise because, clockwise and counterclockwise depends on which side you're looking at it from. So don't fall into that trap. Don't think in terms of clockwise, counterclockwise. That won't work. Right, but nevertheless, thumb in the direction of the surface, normal. Fingers define a swirl, and then just give me 2 seconds. Just ask yourself then, how does that swirl? How does it brush up against that boundary curve? If you were to drag this swirl close, not on, but close to that boundary, which way would that swirl swipe up against that side? That defines the orientation on the boundary. Yes?
I was wondering how you knew that the surface or the end went up instead of down.
So that has to be given. If you're going to talk about the boundary of an oriented surface, it has to be an oriented surface, and you have to know what that orientation is. Yeah. If someone were to come to you with a surface that it does not have any orientation and ask you what's the orientation on the boundary, it's not a well-posed question. It doesn't make sense. Yeah, absolutely. Anybody else? Everybody's happy? It's kind of a weird rule. I will confess there are other versions of this rule that you can write down and describe. I think this is a really good one. So I'm gonna leave it at this. I think this is the best one. I think this is the one that's going to be most easy to put into application in practice. But if you want to see some others, I can show you some others. Come to office hours. Okay. All right. So that's what boundary means. This is the orientation. This is the orientation on the boundary. All right. Okay, so accumulation. Now, again, this is going to look a lot like our argument that we made when we were doing Green's theorem. And let me just slide back. Here we go. Here's where we were when we were talking about Green's theorem. And we had a two-dimensional region. And you can talk about boundary circulation around that surface, around that two-dimensional region. You can likewise talk about boundary circulation around the left side, and you can talk about boundary circulation around the right side, and you can add those up. And the whole ends up being the sum of the parts. And the punchline is that when you look at this shared edge in the middle, if you will, right, as part of the boundary of the left side, it's oriented that way. As part of the boundary of the right side, it's oriented that way. Opposite orientations on the same curve cancel. Right? So that was the big idea. That's the nugget that makes it all work. That's why we look at boundary circulation in the first place. Right? It's because it accumulates, because it works out this nicely. That's what makes the theorem exist in the first place. Okay. So, very, very similar deal here. Again, we're going to look at boundary circulation because, again, it's going to work out that it accumulates. And, again, it's just a matter of kind of drawing the picture and writing it down. If you look at the whole piece of surface there and you talk about the boundary circulation, well, the boundary circulation would be computed along that oriented boundary. Right? Notice my orientations are upward here on this surface. So up, fingers, swirl, side swipes, etc. gives us that. So that's the quantity in question for the whole surface. Now we look at just the left, and that gives us that. We look at just the right, and that boundary circulation gives us that. And when you add those up, I claim that these two edges here, if you look at those two pieces, well, they're on the same curve. The same little curve up here in space. It's just that on the green side, we're going that way, and on the blue side, we're going that way. Opposite orientations, they cancel. And when you throw all of that away, notice what you're left with is exactly the boundary circulation of the whole. So again, the whole is the sum of the parts, aka it accumulates. Everybody on board? Okay. All right. So I think it's very helpful, again, to think about how this compares with Green's theorem. It's a shockingly similar picture. It's almost exactly the same story. In fact, I like to point out that if you were to draw this diagram on a piece of paper, then you can take that piece of paper and then just lift it up off the desk and do about like this. And now you've got a three-dimensional model of the argument about Stokes' theorem. It's really the same thing. Okay. All right. Okay, so we have an accumulating quantity. All of the same goodies come as a result. You can slice up as many times as you want. Doesn't matter how many pieces. You slice and dice all you want, right? And each one of these little shared edges, each one of these interior edges, like let me switch to pencil. Like this edge right there. Right, well, I'm going to zoom in so we can see better. And, well, as part of the boundary of this left side, it's oriented that way. As part of the boundary of the right side, it's oriented that way. Opposite orientations on the same curve, line integrals have opposite signs. They cancel. Poof. So, slice it all you want. It doesn't make any difference. And I can talk about then, I've made this observation before, but even though we compute boundary circulation on the boundary, thus the name, boundary circulation, you can choose to think of that boundary circulation as actually coming from pieces in the interior, right? And so, for example, if I'd like to know how much of this boundary circulation that I've computed on the purple, how much of that comes from inside of this little green box, well, this circulation that I'm representing right there, that tells you how much of the circulation, of the purple circulation comes inside of that green box. And if you want to know how much happens in this blue little piece of surface there, well, The amount that comes from the blue piece of surface. Well, whatever this circulation is there, right? And the whole is the sum of the parts. And so how much you see on the boundary that comes from each of these pieces, you can just compute as those individual circulations. Again, not that you have to look at it that way, but that you can look at it that way. And it's very helpful, and so you should look at it that way. Okay. All right. So, again, just like with Green's theorem, our accumulating quantity, it behaves like stuff. Right? I mean, this is how mass works. All right, just a reminder, I know I've said this before, but if you have a mass, and you ask, what's the mass of this lump? Well, if you cut it in half, there's a mass at the left side, and there's the mass of the right side, and they add up to the mass of the whole. And if you want to know how much of that mass of the whole was in the left side, you can just look at the mass of the left side. I mean, it behaves exactly the same way. And so if it behaves like stuff, you can pretend that it is stuff. Treat it like stuff. And accordingly, then, we're going to talk about this kind of a density, stuff per unit size. Remember, that's what density is. Stuff per unit size. So the associated density here, circulation per unit area, is something we can talk about. And here's the formula for it. Don't worry about where this formula comes from. There's some kind of tedious calculations that go into confirming if this is the formula. Not really what I want to focus on. Far more important than where this formula came from is how to interpret it. In particular, I want you all to think of this, again, wherever the formula came from. What it is it's telling you how much of the total circulation that you're measuring came from inside a given little piece of area. All right. Okay. Pausing. Questions? Everybody okay? All right. Okay, so now there is something weird about this. If you look at this formula for density, and let's compare it to the formula we saw with Green's theorem. Here it is. Our circulation density for Green's theorem. You'll notice that this Green's theorem circulation density depends only on the vector field. Right? You give me the vector field, I can compute Green's operator. I don't really care which region or around which curve. None of that matters. Domain doesn't matter to compute circulation density when you're doing Green's theorem. It's just that the density is independent of the surface, of the region or the curve that you're looking at. Likewise with the divergence theorem, think about it, right? Your density there is divergence. We have a formula. It only depends on the vector field. You got to know P, Q, and R. You take the appropriate partials and what solid you're looking at. We'll deal with that later, but the density itself depends only on the vector field. So what's weird here with Stokes' we're in the process of developing something called Stokes' theorem. But this circulation density, you'll notice it depends on the vector field. This part here depends on F. But notice, there's also a part here that mysteriously depends on the surface. Right? And that's a head scratcher. That's weird. It's very different. And so for the moment, I'm just going to make this observation and kind of let y'all be kind of wondering about that. I'm going to come back and deal with it a little bit more carefully in a few minutes. But that is a little bit weird, that there is a orientation dependence on that density. Okay. Alrighty. So we are now ready to put it all together. Circulation is an object of interest. Let me see if I can get that. There we go. Circulation is an object of interest. Boundary circulation, of course. It accumulates, as we showed. So we can chop it up into little pieces, and the whole is the sum of the parts. Also, as a result of the fact that it's an accumulating quantity, I can talk about its associated density. And here it is, reminder, just from the previous page. That's what the density is. Density is curl F dot N. That gives you, of course, stuff, aka circulation, per unit size, aka surface area. Stuff per unit size. So that's our density. And you could draw a line right there and call that Stokes' curl theorem, and that is fine and dandy. And some books write it that way, and there's nothing wrong with that. So Stokes' curl theorem. Notice again, there's kind of the three steps. There's the identifying that you have an object that can be viewed as a quantity, viewing that, realizing that is an accumulating quantity, identifying what the associated density is, and then you've got a theorem. Okay, how are we doing so far? Now, I like to pull a tricky move. Y'all have seen this before when you have an integral that looks like this. In particular, when you have n vector ds scalar. Recall that is our ds vector. And I like to, when the opportunity presents itself, when you have in other words, a flux integral, a vector surface integral, it looks better, if nothing else, to rewrite n ds as ds vector. And the case that I've made previously is that, well, yeah, because, this is part of the domain in some sense. It comes from the domain. It's describing a piece of the domain. And so does that. So does the n. Right? All of this stuff over here is telling you about little pieces of the domain. By contrast, curl of the vector field has never heard of your domain. The vector field exists independently of your domain. It's a totally disconnected thing. And so I think it looks better on the page, if nothing else, but it's also just more natural to write it like this. Okay, so this is the way I prefer to present Stokes' theorem, and that it is this right here. Everybody all right? Okay, so let's see an example. Before we get into how to solve this problem, let me point out something about the statement of this question. Notice it asks you to compute a line integral, and it gives you a bunch of specifics, right? There's a formula for the vector field, and there's a curve. But notice it doesn't say anywhere in the question how you should compute this line integral. It just says compute the line integral, and you figure it out how to do it, right? So this is how stuff goes down in the real world. Very rarely does the problem come with the method of solution attached to it, right? So I'll just point out that when you see something like this, you should consider all possibilities, right? How do we compute line integrals? Well, gosh, we've got several different methods. One is to parameterize and pull back through the parameterization, right? What is that? Chapter 6, right? So you could just plug and chug, as it were, f dot x prime dt and all that. And that would get you there. I'm not saying that'd be nice. I think that would actually be a little bit annoying in this case, but it would. If you can do that integral, then that's that's fine. Hey, here's an idea. Line integral. How about we use the fundamental theorem of line integrals? Right, fundamental theorem of line integral is pretty awesome. That's another candidate. You should entertain the possibility of using the fundamental theorem of line integrals. Now, it's going to turn out, in this case, that the fundamental theorem of line integrals won't work. There is a catch. Don't forget all these boundary theorems, all these accumulation theorems that I'm presenting to y'all. They all come with a catch. In the fundamental theorem of line integrals, the catch is that the vector field has to be a gradient. And as it turns out, this vector field is not a gradient. And we're going to see why soon. Okay. All right. Okay, so plug and chug, pull back through the parameterization, looks hard. Fundamental theorem of line integrals, not on the table. So, for lack of good alternatives, let's try a different approach. Let's see if maybe we can use Stokes' theorem. And again, here it is. Can we use this? After all, it does say it can compute line integrals. There it is. Again, catch. Oh, yeah, question.
Is there a trick to know which one, or do you just try until you...
So I have a strategy that I use for trying to make such decisions. It's a great question. I'm going to, once we have all of our tools put together, I'm going to talk a lot about how should you go through that decision-making process. Great question, and we're going to talk about that later. Yeah, absolutely. Okay, this says we can compute line integrals. Cool. Again, it has a catch. All of these awesome theorems have a catch. This one, the catch is visible already right here in what I have circled. Notice it says right there, it's got to be a boundary. Stokes' theorem will not compute just any old line integral. It only computes boundary line integrals. Okay, so now again, is this just mathematicians being uptight? No, not at all. And I want to emphasize, and I've made an analogous observation every other time we've talked about this sort of phenomenon. Your curve has to be a boundary of a surface because that surface is the surface through which you would compute the corresponding flux. So if your curve is not a boundary of a surface, then it's not a question of whether this integral equals this integral. It's that there is no such surface integral because there is no surface. Because your curve is not a boundary at all. So this is again this is not a sort of a regularity thing. Oh, it's got to be continuous or something like that. No, this is a massive crash and burn faceplant nonsense, useless, nothing, nowhere, unless your curve is a boundary. Does that make sense to everybody? Okay. All right. Alrighty, so we got to turn back to our example and ask ourselves, is this curve a boundary? Okay, well, we better figure out what this curve actually is. You look at the parameterization, you recognize it as being very reminiscent of our old friend, the unit circle. You see that z is equal to 0, so this is in the xy plane. This minus sign just means that you're going around the other direction. We're literally reflecting there. And so our curve, without too much trouble, you can persuade yourself. The curve is about like that. Everybody with me on the curve? Now, reminder, what we're interested in right now is trying to identify if this is a boundary. It's very tempting to just say, yeah, look at that. That's the boundary. That's where the ant gets confused if he's walking around on that yellow surface, this sort of unit disk in the xy plane. But remember, everything's got to be oriented, right? So I need to know what is the orientation on this yellow surface. In particular, what is the orientation on this yellow surface that results in the ant getting confused on the purple curve with the correct orientation, right? So this purple curve is given with an orientation that comes from the parameterization. This implies an orientation specifically in the way that's drawn. Right? So we got to get the orientation of the surface correct. And my favorite way to do this is I'm going to say trial and error, but just keep in mind when you're talking about orientations, there's only two options. So it's not going to be a hard trial and error. It's just, try one. If it doesn't work, it's the other one. So pretty straightforward process. Let's see how that plays out. Let's first entertain the question of maybe, let's see here, I'll use this color. Maybe the orientation is up. Okay, well, could that be right? Well, let's play the game. If our surface orientation is that way, right, and you look at your fingers and you think about the way that they swirl, that would define a swirl going like so. If this swirl that I've got defined there, if that were to sideswipe up against the boundary curve, would it be going the correct direction? Nope. It's just going the wrong way. So what that tells me then is that that's the wrong guess. I guessed wrong. What do you think? Does everybody follow that process? Yep.
How did you know that the curve was going
Yeah, great question. Okay, so how did I get the purple orientation? Yeah. The purple orientation comes from, it comes from the parameterization itself. And in particular, knowing position as a function of time, you can take the derivative of this, and that would give you the velocity, and that velocity defines the orientation. Yeah. And so, you could explicitly punch that out, and you would notice that you get this as an answer. You can also, though, remember that if it's cosine t, sine t, then you just remember. We've seen that one before, and that would be going the other way. And this minus sign means that we're reflecting, and that reflection turns one orientation into, the opposite orientation. Does that make sense? Yeah. Cool. Great question. Everybody else good? Okay, so reminder, we know that this in some sense is the surface that we want, but we got to figure out the deal with orientation. We entertained the possibility that maybe this might be right, but no, it wasn't. That was wrong. So process of elimination, I kind of know that my orientation has to be the other way, but let's think it through just to double check. Okay? So if this were our orientation, forget about the blue. If this green vector is our orientation, thumb in the direction of the orientation, you look at the right hand. By the way, it's got to be your right hand. Right? Be very careful about that. If you have a pen in your right hand and decide to use your left hand instead, not going to work. So right hand, thumb in the direction of the surface orientation, your fingers of your right hand will point in a direction defining a swirl. Does that sideswipe the correct direction? And yes, indeed. Yes, it does. So that's our normal vector. How we doing? Everybody happy? Okay, so we have a boundary. Let's see here. Purple. Our curve is a boundary. And yeah, you got to pay attention to the orientations, but knowing that it's a boundary, right? Realizing that the curve that we were given is the boundary of a surface that we now understand. We can just invoke Stokes' theorem that says that boundary circulation is the flux of the curl through the anti-boundary surface. And now we've transformed our question from a line integral question into a flux integral question, and now it's just a question of how are we going to compute this flux integral. And I'm going to say it's all downhill from here, and we'll do those details. But before I get to that, I want to make sure everybody's happy with how we turn this into a flux integral. Okay, all right. So, what to do with the flux? You'll notice here, by the way, I did not write this in the usual ds vector notation. I wanted to see my unit normal vector there because, again, in this case, I already know what it is without parametrizing the surface or anything. And so, who knows? Maybe this will work out conveniently. This flux integral will work out conveniently without having to parameterize and play the usual game. And in fact, in this case, it does. Look how nice the normal vector is. It's just 0, 0, -1. And similarly, I can compute the curl here. This ends up being 0, 0, 2. And that's the simple matter of taking your given vector field and following what it says. We're taking our vector field, we're computing the curl of it. So various partial derivatives and this one minus that one. And y'all remember that whole kind of, it's a symbolic cross product, which is a symbolic determinant. Right? Anyway, there's a formula there. And punch it out, and your curl is also constant, 0, 0, 2. And so altogether then, this dot product is just -2. We have a very convenient little integral here in that this is a constant integrand on a garden variety surface whose area we already know, and we win. What do you think? Everybody happy? Okay. All right, so that's Stokes' curl theorem. Now, there's some other things to say. I swept under the rug here when we were talking about density. What the deal is with the circulation density depending on the surface, and that was strange. So back to this point now, and how to make sense out of that and what to do with it. I'm going to point out that in fact we have seen this before. This is exactly the circumstance that we saw when we were looking at the fundamental thermal line integrals. And I just kind of blew over it at the time. I said a couple of words, but here we are again, back to the fundamental thermal line integrals, and we wrote down. That's our DFDS, if you will. That's what gives us change per unit size of a little piece of curve. So that's our scalar change density. We wrote it down like that. And then, you may recall, we made some similar gripes, and we're like, well, this kind of comes from the curve, but then again, so does that. All of this together really is telling us about our little piece of curve. Why don't we lump that all together and call it the dx vector, right? And this, of course, is just our position differential. It's literally our displacement along that little piece of curve. But we can lump that together. Now, if you look at, let's see here real quick. Let me highlight again. If you look at how we interpret densities, in the same sense that this is a scalar notion of size, and so we call this a scalar density, well, likewise, this is an oriented notion of size, you might say, right? If you're willing to play along, further generalize our idea of density as, it's not just mass per unit volume, it's not just stuff per unit volume, it's not even just stuff per unit size, but we could even say it's stuff per unit oriented size, right? Just further generalizing. Then this thing here, if you accept the ideas of an oriented size, then this is your corresponding oriented density. Everybody remember that? Okay. All right, so you have to kind of, again, broaden your point of view about what the word density ought to mean. And then, now let me further remind you, and this goes back to chapter 2, the gradient vector. Conveniently, our oriented density is a familiar object. It's our old friend, the gradient vector. We can break that down, and just remember from chapter 2, we already know stuff about the gradient vector. The magnitude is telling you how steep the hill is. Right? Now, keep in mind, I'm not walking up the hill. Uphill maybe is that way. I'm not going to walk straight up the hill. I'm going to zigzag. I'm going to do switchbacks. Right? And I'll be zigzagging around. So I'm not going straight uphill. But if you ask the question, how steep is the hill itself? No, the magnitude of the gradient tells you how steep the hill itself is, independent of my own path and my own experience. Right? And then further, the direction of the gradient is telling you which direction is uphill. Which direction do you go to experience that actual steepness of how steep the mountain actually is. All right, so two things, sort of a two-step process here. We reinterpret size and then accordingly reinterpret density from a sort of an oriented point of view. And then secondly, recall, that we already know stuff about this vector, and namely we know stuff about its magnitude and we know stuff about its direction. Okay, so I'm going to do exactly that same thing now, and I deliberately laid this out on the page in the exact same pattern now. But now this is Stokes' theorem. So reminder, circulation accumulates. Density and all that. Right? And if you have, again, a scalar notion of size, then you get a corresponding scalar notion of density, and there's what we call our circulation density. And this is where we started to get uncomfortable and say, well, yeah, but it depends on the surface. This is not independent of the surface. That's weird. So, again, then, I'm going to look at the parts that do depend on the surface. I'm going to lump them together. This is our familiar ds vector, right? And now with that having been done, let's not ask circulation per unit scalar notion of size. Let's ask circulation per oriented notion of size. And that then oriented density is just kind of what's left over after I've already sort of absorbed that normal vector into the ds vector. And so this is what we call our oriented circulation density. All right? Is that good for everybody so far? So, this is an interpretation you can make of curl. And what do we know about curl, and how do you think about it? Well, it's the thing that you multiply by oriented size to get circulation. It's circulation per unit size in an oriented sense, and so it's oriented circulation density. So that's a meaningful natural answer just right there. Okay. By analogy with what we have up here. Remember, our oriented density there, we broke it down into a magnitude and a direction, and we recognize that the magnitude has a natural meaning and the direction has a natural meaning. I claim something very similar is going to happen here as well. Curl, also, you can break that down as a magnitude and a direction. And they both have a natural meaning. Now, these are not natural meanings that we've seen before, and I'm not going to prove the interpretations that I'm going to take here. I am going to give you a kind of a plausibility check, right? I'm going to show that this kind of tracks with some examples, and this does what it's supposed to do. And I'll give you a couple of those examples, but I'm not going to prove the features that I'm about to describe. But here we go. The magnitude of the curl. It's telling you, in some sense, how much of a tornado do you have there, right? Keep in mind, we're talking about a fluid that's rotating around. There's sort of a rotational aspect to the fluid. It's tornado-like or whirlpool-like or whatever you want to call it. And that magnitude tells you how strong is the tornado. Is there a lot of circulation or just a little circulation? Kind of analogous to how the magnitude of the gradient tells you how steep is it. Is there a lot of steep or just a little steep? We know the gradient means steep. It says something about steep. Magnitude says how much. Likewise, curl is talking about rotating fluids, rotation in the vector field, and the magnitude of the curl is what tells you how much. Likewise, in the same way that the direction of the gradient tells you what the direction of that uphillness is, likewise, the direction of the curl tells you the direction around which that whirlpool or tornado is happening. Right? So now again, I'm not going to prove those claims. These are just claims. But here's the picture. Your curl vector, I'll do this with the pencil. Your curl vector is something like this. Right? The magnitude is telling you how much tornado are we seeing there. Longer curl vector means there's a lot of rotation of the fluid. Shorter curl vector means there's a gentle rotation of the fluid. The direction, so whatever unit vector you might say, points in the direction of that curl, defines the axis that rotation is happening around. So in this case, as I have it drawn there, it defines that axis. Yes?
I'm just wondering what you mean by gentle rotation versus massive rotation, kind of what that would look like.
Yeah. So I mean, in terms of what it looks like on the picture, in this particular picture, it might manifest, for example, with kind of shorter arrows, right? In other words, that the if you were to follow the path of a particle that's following the fluid, like what they call from chapter 3 we defined line of I can't remember what it's called. What am I thinking of? Where you follow the path that the particle follows the fluid. Flow line. Thank you. I don't know why I couldn't think of that. So the flow line here is going to be kind of circles, right? Heavy curl, lots of curl, would mean that it's going around that flow line faster, if you will, kind of. And a shorter curl vector would mean that it's kind of only slowly going around. And that's what it for this particular example, that would be the interpretation. I mean, I do want to point out not all vector fields that have curl are going to have circular flow lines, right? But it's going to be that kind of thing. Alrighty. Now again, not going to prove these claims, but I do want to kind of show you how this, they look to kind of make sense. And these two examples here, and just to be clear, to distinguish these, I'm going to draw a line right there. This is two separate examples. We have here the same vector field, and I just want to talk about how the same vector field would create circulation by different amounts in different cases. So we have two different little pieces of surface, and we're going to talk about what the circulation story is with respect to this exact same vector field for both of these. And let's start off with this one here. So there's a surface, and we can talk about its boundary curve. And the surface, of course, has an orientation vector. Right? And so this being set up as it is, first question, how much boundary circulation do we kind of expect to have? Keep in mind, the boundary is kind of going around like that. Notice as well, the fluid is doing kind of the same thing, right? The boundary curve is going around like that, and the fluid is going around the same way. So you should expect to get a lot of circulation of this vector field around that boundary. Because, the vector field is following along perfectly with the boundary. Does that make sense to everybody? Now, I claimed that curl dot normal vector is what's going to pick that up. Curl dot normal vector is telling you, but how much are you over the interior? How much circulation are you actually sort of getting everywhere in that interior? So how do the curl and the normal vector pick up orientation in this picture? And notice curl and normal vector parallel. So you expect this dot product, this blue dot product, should also be large, corresponding to the fact that, yes, we are picking up significant circulation going around that boundary. Does that make sense? Okay. Now, by contrast, let's look at the other scenario. In this other scenario, same vector field, same circulation, or same rotation of the fluid. Here, though, we have a different piece of surface, a different orientation. Obviously, it's also got a different boundary, right? And now let's kind of think through, are we getting circulation here? How much circulation are we getting? Well, we're not really getting any circulation here at all. The fluid is circulating around that way. The boundary is going in a different direction. And if you specifically were to look at the vector field arrows themselves, these field arrows like that over here, they're like that, and they're perpendicular. The curve is going that way, the field is going that way, we're not picking up any circulation over here. And then likewise on the backside, there, it's just going the other direction, but still perpendicular. So we don't expect to get any significant circulation. There's just not any circulating happening. The circulation's happening in a different direction than this boundary piece of surface is itself going. So nothing. And then analogously, let's see, how much of what we claim here is picked up by the dot product. Well, the curl is going that way. The normal vector is that way. Again, perpendicular. So we don't get any of that dot product either. Right? So in both cases, this dot product, curl dot in, is, it corresponds to how much of the circulation is actually happening around the boundary itself. And the more that our surface kind of turns around like this, the more then that the circulation actually picks it up, well, then the more that this dot product is going to go positive, get larger as well. So anyway, that's just a plausibility argument. I hope that kind of, somewhat persuasive perhaps. But this is the justification then for, my claim that what curl is. Curl defines an axis of rotation and in some sense by its magnitude a measure of how much rotation the fluid is doing. And we seem to be out of time. So we'll draw the line right there. And see y'all on Wednesday. Again, welcome back. Hope you had a good break. And stick around if I didn't get you for attendance at the start of class.